But before we move towards the types of the activation function, let's first understand that what this activation function means. So actually the name suggests that it is activating something. Okay, I don't know what that thing is, but it is activating something. For example, there is a person and you have a machine, okay, and that machine tells you that whether you should go towards the party and whether you shouldn't go towards the party. Okay, and on the basis of certain inputs it is telling you this. So for example, if you just want to put the machine and you feed it with the, for example, of your willingness to go towards a party of, for example, 30%, you have a willingness to go towards a party. So on the basis of that it will tell you that you should go or not. For example, you have a 50% willingness to go towards the party, so it will tell you that whether you should go or not. Actually the activation function takes an input and it gives you an output on the basis of which it activates something. So we have actually three types of the activation functions: the binary activation function, the linear activation functions, and the non-linear activation functions. Okay, I will just explain each and every one bit by bit. Okay, so the first one is the actually the binary function. Okay, so the binary tells you that it will have two outputs, 0 and 1 by 2. Okay, so 0 and 1. As you can see over here, the graph is just showing you that the output will be between the 0, the 1 and the 0. Okay, just this, in this range. Okay, you cannot move out or from this range. Okay, so this is actually telling you that this will be in the range of this output. Okay, the function tells you that it is a simple function that outputs either 0 or 1. Simple. Okay, now here is a sentence: not used in modern deep networks due to the lack of gradient. So actually the gradient is just telling you the slope of that function when you just want to back propagation. In the back propagation topic you will learn that how we use the back propagation or the gradient descent in order to minimize the error and improve the accuracy of the model. So actually there are only two outputs, so how we could calculate the accuracy and the slope of the gradient? So it's not easy to calculate the slope of the gradient. Okay, so that's why we don't use this. And here is a function, and it is actually a pair function. When you have this kind of function where you have the uh, where you have the conditions for something, so it will just call as the pair function. Okay, so this was a simple binary function. Now we have the linear function. As the name suggests, that it will be just a linear. So whatever you put into this function, whether you are putting the 1, 2, 3, so it will output that number as it is. So if you are putting as 2.5, okay, if your x is 2.5, you will get a y as also 2.5. If your x is 5, so your output will also be a 5 number. Okay, so it is actually a linear problem. So but it is not used in many deep learning problem or where you have the complex patterns, but it is used in some sort of linear regression problems. Okay, so in order to find the linearity between the x and the y values. Okay, simple. This is a linear activation function. Then we have the sigmoid function. As the name suggests, that it will be just like s. Okay, the graph is just like the s, as you can see over here, that this is a smooth graph. And this function actually gives you the output between 0 and 1. Okay, now you will ask me that it is also giving me the output between 0 and 1, and the binary function is also giving me the output between 0 and 1. So what's the difference between this and the sigmoid activation function? So actually in the binary, when you have the output between 0 and 1, for example 0.6, 0.4, you cannot achieve that 0.6, 0.4, 0.2. You will just achieve 0 and 1. Okay, but here in the sigmoid function you can achieve the values between 0 and 1, like the 0.2, okay, the 0.4, the 0.6, and the zero point 0.7, the 0.7, 0.73, etc. Okay, so all of these are achievable in the sigmoid function. So it is actually better version of the binary function. And you can see over here that the function is just saying 1 over 1 plus exponential power minus x. So actually this exponential is adding the smoothness to this curve. As you can see over here that it is a very smooth curve. Okay, so in order to aid the smoothness to this curve between transitioning from 0 to 1, so when it is transitioning from 0 to 1, as you can see over here that this is a very smooth curve. Okay, smoothly it transitions from 0 and 1, so due to the e power minus x. Okay, so this was about the sigmoid. Then we have the tangent h, or you can say like the hyperbolic tangent function. As the name suggests that it will be a tangent, so the tangent, you know that it also, it gives you the output between plus 1 and the minus 1. Okay, simple. So it is also a more better version of the sigmoid function. So actually the sigmoid function gives you the output between 0 and the 1. Okay, but the tangent activation function gives you the output between plus 1 and the minus 1, as you can see over here, that this is also giving you the outputs between the zero point 0.5, the zero point 0.5, the 0.25, etc. All of these are the values between 0 and 1, and it is also giving you the minus 1 and the 0. Okay, so it is a more better version of the sigmoid function. Okay, as you can see over here that it is not just the e power x is not only in the denominator, but you can also see that it is also in the numerator, and due to this you can also get the negative version of this function. Okay, then we have the rectified linear unit. So actually the a rectified linear unit actually gives you the output if the input is greater than 0, and if the input is less than 0, it will just gives you 0. As you can see over here, it is giving you only and only 0 if the output is less than 0, and if the output is greater than 0, it will just give you that same output as it is. Okay, don't worry about that. So actually if you can see over here that the max function over here, so the max is just looking over the parameters. There are two inputs. So if the x is greater, okay, if the x is for example the 2, if the x is 2, so it will just look out that which number is maximum. So 0 is not maximum, so the 2 is maximum over here, so it will just take the 2 and plot it over here. Okay, and if you have the for example the minus 2, so as you can see over here that the minus 2 is less than the 0, so now the 0 is maximum, so the max function will take the 0 and it will output as it is, and that is the dead neuron problem. Okay, what is mean by this dead neuron problems? If we have certain inputs or x which is, you know, the less than the 0, and that inputs are having some sort of connectivity with the output, and it's some sort of impact on the output, but we are making them 0, it means that we are affecting its result. We are affecting the result of our output on the basis of these dead neurons, because we are making them dead if this is less than 0. So it is a very bad problem for us. Okay, in order to improve the ReLU function, we have just announced the leaky ReLU function. It means that we are just making a leak in the ReLU function, and we are just allowing the some sort of negative values. For example, you can see the difference between the leaky and the non-leaky, or you can say that the ReLU function, that the ReLU was just on the 0 line, but you can see over here that the leaky ReLU function is just a little less than the 0 line. Okay, what is saying that it is just allowing the negative values to pass on. Okay, that is just happening due to this alpha value. And what is this alpha does? The alpha is multiplied with the x. Okay, if it is less than the 0. Okay, so in the ReLU function, if it was less than 0, it would become 0, but now it is just multiplying it with the alpha. Okay, so the alpha is just, you just provide it as in the beginning of the start of the activation function. Okay, Then we have the parametric ReLU function. So it is just like the leaky ReLU function, but the problem is that the alpha over here is just learned during the training of the model. So when you are training the model, due to the loss function, it is just updating the alpha value, and when it is updated during the training, so your model output improves and improves and improves, okay, over and over. This is the only difference between the ReLU and parametric function. As you can also see that it is now allowing more negative values to just pass on this function, okay. Then we have the exponential ReLU function. The exponential is just adding a smoothness or a smooth transition between from the positive to the negative. As you can see over here, all the other graphs that they are not that much smooth. There is a solid curve between the zero and the negative values and the positive values. But you can see over here that there is a smooth curve, just like a sliding bar for kids. I'm kidding, right? So it is just like a smooth curve for that purpose, and it is just because of this exponential function. So whenever you see this the exponent in any function, you will just have to understand that this is adding only the smoothness to the curve, okay. Then we have the softmax activation function. Okay, so what is that? Softmax activation function is just like the probabilistic functions, or you can also say like when you have the probabilistic models where you just want to predict the probability of each and certain outputs. So it is used in that scenarios. It is just dividing a value input with the exponent of its all numbers. It is actually the summation. So the summation means that all of the values will be divided on it. If you divide it on this, so it means that it will the summation of all the probabilities will be equal to 1, okay. This is the definition of the probability, okay. Then you have the Gaussian error linear unit activation function. You can see over here that this is just like a ReLU function, nothing more. But here the little curve over here is what make it Gaussian error linear unit. And what does the stochastic regularization means? The stochastic means that it is used for in the cases of when you have the data having many randomness in that data. There is a very is complex patterns in that data, and you have to regularize that. And regularize means that you just want to normalize that data because due to its randomness. So this function is really helpful for that, in order to do that. So, and you can see over here that the tangent is I have told you that the tangent h is just used for the output between the 1 and 0. It is not actually the output between 1 and 0, because you can see over here that the zero point 0.5 multiplied by x is just exceeding it from the 1, okay. But it will always tend to make the output between the 0 and close to the 0 and 1 as much as it can do, okay. Then we have the swish activation function. It is just like the sigmoid function, but you can see over here that there is x multiplied with this one. There is an x which is multiplied with this one, and you can see over here that this is performing better than the ReLU function, okay. So this is a more better version of the ReLU. Then we have the scaled exponential linear unit. Have you have seen the exponential linear unit where you have the graph like this? Okay, this was for the exponential unit, exponential function. But here the scaled means that we are just multiplying the exponential value with the alpha, okay. This is the difference between the exponential and the scaled inputs exponential values, okay. So in order due to which we have a more smooth curve, and we are just allowing more negative values, okay. We are just allowing more negative value to just pass through this function due to this scaled version. So this was all about the activation functions and the simple activation functions. There are a lot of activation functions, but these are the most important and which we use in the common the problems of our deep learning, machine learning, etc. I hope you got something new in this video. If you like the video, so hit the like button and subscribe to my channel in order to be notified for every new video on the basis of artificial intelligence and the mathematics. Thank you and have a nice day.